My name is Itamar, and today I'm going to be talking about vectorization, or how slow Python runs fast code. And before I start to talk, I'm assuming here that you're working on software that doesn't hurt people, it doesn't hurt the environment, that is positive or at least neutral on its effects. And if you're writing software that is not the case, that is somehow harmful, like before you make your software faster or better, it'd be better to find a new job and then apply those new skills in a positive way. So taking that as an assumption, why would you want your software to be fast? You may have a deadline. Your software may have to complete within a certain amount of time. You might have a user who's expecting results within 10 minutes. If you use less hardware, then this can save your employer money because you don't have to pay cloud computing. You don't have to pay for more servers if you're using your own machines. Reducing electricity use means reduced carbon emissions. You can also check if your data center is using green energy. But insofar as energy is fungible, in general, reducing energy use is a positive thing. And finally, and most selfishly, working on slow software is not fun. If you're talking to your manager, you can talk about developer productivity, but really it's not a fun experience to develop and improve slow software. And you can think about this in terms of cycle time. Like, how long does it take you to add a feature? How long does it take you to fix a bug? If it takes you a day to know that this experiment failed, that there's a typo that's going to invalidate your results, then you can only do like a handful of experiments every week. If you get it down to an hour, now you're doing multiple experiments a day, and so on and so forth. And so improvements in speed can enable you to make changes and try experiments and improve things in ways that would be impossible with slower software. Like, there are things you will do if you know it's going to take you 2 days to know if it actually worked compared to an hour. And so faster software, in the end, allows you to also build better software. Which brings us to Python. Python is slow. And it's also a popular language for doing things like data science and scientific computing and other forms of data processing. And the thing about data processing is, as you can tell from the name, it often involves a lot of data. And processing all that data is slow. So how is it that you can get fast results from a slow language? How is it that Python, which is slow, is so popular for data processing? And so to sort of scope the discussion, the area this talk is going to talk about, if you think about geographic weather readings, like you have all these sensors scattered in space, and like maybe in like clouds, and you have some on the ground, and you're measuring temperature, and you're measuring air pressure and humidity, and you're doing this over time. You can do spatial gene sequencing. You have this little tiny tissue sample, and you're like shooting lasers at it and taking photos, and you have get this 3D image of where the genes are expressing. You have this time series of a stock, it goes up and down over time, or a data frame, which is mapping from column names to essentially one-dimensional arrays. All of these things are basically underneath the hood can be expressed as arrays. And so the infrastructure that makes Python fast depends on the domain. And in this case, we're focusing on the kinds of applications that involve processing large numeric arrays. And the general idea, and the talk will go into much more detail, is that you can make all kinds of general purpose array operations. You can think of a sum, a mean, and so on and so forth. And you can implement those in a fast language. Traditionally, this would be C, C++, or Fortran. These days, I would suggest Rust is a much better choice than C or C++. You take those operations and you expose them to Python in a library, NumPy, SciPy, Pandas. And this is a strategy that goes back more than 20 years to the original numeric libraries for Python. And then you can use those generic functions in Python code to assemble the actual high-level logic that you care about, the algorithm that you care about. Because there's no reason for you to implement sum and mean and so on from scratch. You can use this library, which is fast. And so all your data processing happens in a fast language, say C. And then your high-level control and logic is in Python, which is a much nicer language to write than C. And it's worth making, when we talk about like Python being slow and vectorization, which we'll define later, but just assume that there's some way to make things faster. Like, it's worth looking at an example and saying, how much faster can. And so we want to calculate the mean of a NumPy array. It's an array of numeric data, say lots of integers, lots of floats. So the way you calculate the mean is fairly straightforward. And these two different ways of doing it are semantically identical. They will give you the same result. So if we just use a for loop, we start with a total of 0. And then for every index in the array, we add the value, that index, to the total. And then we divide the total by the number of entries in the array. This isn't quite idiomatic Python, but it's sort of a closer mapping to the way you would do this in a lower level language with explicit indexing. So you sum all the items, divide by the number of items. The other option is you can use NumPy's built-in sum function. So we can say the total is numpy.sum of the array, and then we return the total divided by the number of items in the array. And this sum function, the numpy.sum function, is where the magic happens. And again, you get the same results if you run these functions. There's no difference. Semantically, they're the same. And this is one of the critical points about writing fast software is when you start thinking about speed of software, implementation details matter. You can't just say, oh, this is a black box, I don't have to think about it. You actually have to think about how things are implemented if you're going to write fast software. So the two functions are the same semantically, but the speed is very different. So I took an array of 30 million random integers and measured it two different ways, once with a for loop and once with the numpy.sum vectorized implementation. And you can see the second version is 100 times faster. And here it is again in bold and italic, just for and some exclamation marks, 100 times faster. And much of the time, the sort of speed ups you get might be only 20 times or 30 times faster. But honestly, that's great. If my software runs 20 times faster than I started, I'm very, very happy. Really significant speed ups to the point where if you didn't have the ability to use something like NumPy for this sort of operations, you would not be using Python for these sort of calculations. It would just be unusable. Like a thing that would take you a minute with NumPy would take you an hour and a half with pure Python. Like it's just not viable. And so these speed ups are critical to making Python usable for data processing. And so for the rest of the talk, we're going to dive into why Python is slow. We'll talk about a better data presentation for arrays, which enables us to use faster operations, so-called vectorization. And then we'll talk about how to write fast code using vectorization once we understand what it means. And in fact, there's multiple meanings, and so you have to be careful, a little bit careful about that. So we'll start with talking about why Python is slow. And to just again, scope the discussion, I'm talking about the default Python interpreter, sometimes known as CPython, the one you would download from python.org or install from Ubuntu or install from Homebrew. I am not talking about the PyPy Python interpreter, which is an alternate implementation. And I'm also scoping this to the existing versions of Python. There's currently an effort on to speed up Python. Conceivably, in 10 years, none of this will be true. But for now, the default Python interpreter you're using every day is going to have the issues we talk about. So we were previously looking at summing an array of integers. And so let's dive into that a bit more. So there's two things that we're doing here. First is we're iterating over the array. Like we're taking first item, second item, third item, fourth item, and so on. And then we're doing some very simple math. We're adding up numbers. So we're going to compare you do this in a low-level language and how much work it is versus a Python implementation. So here's how you would iterate from 1 to, or I guess 0 to some number in C. And C does have for loops, but I'm using a structure that's a little bit closer to the machine code that would get generated. So we get the length of the however long we want to iterate for. We have I equals 0, and as long as I is smaller than the length, We do some work. In our case, it'll be looking up an item in an array and then adding it to the total. Then we increment the integer. And when you compile this to machine code, the CPU instructions that get used are mapped pretty directly to the code. So there's a comparison between two numbers, and there's a CPU instruction for adding a number, but you only do like a handful of CPU instructions for every iteration through this loop. And your computer can do billions of CPU instructions. If I'm doing the math right, large number. So just doing a handful of CPU instructions per iteration, that's nice and fast. You can iterate really quickly. If you compare this to Python, however, things are a little less nice. So in every iteration over a range object, which is how we would go from 0 to n, CPython is going to call the next function for that object. It has to figure out which next function to use, and that can take work. That's something Python might optimize over the years, but that takes work. And then it calls the function. So function call adds more overhead. That's some more instructions that we didn't have to do in the C version. And then it does some comparisons here, and it's doing a little bit of math, and that actually isn't too bad, right? Those are just a few CPU instructions. But then we have this pylong from long function. And so let's look at that. So this is longer. This is doing a lot more work. And remember, it's doing this for every iteration in the loop. And what it's doing is it's taking a C integer, long because of historical reasons, and turning into a Python integer, which is a pylong object star, a pointer to a data structure that gets allocated. So there's some work to allocate the object. For small numbers, it's optimized, but larger numbers, it's not. And you can see it's doing a bunch of work here, and it's calling into other functions that do additional work. There's a bunch of branches, and hopefully the branch predictor in the CPU will get it right. It's just doing a lot more work, though. And so just iterating in Python is doing way, way more work than something written in a low-level language like C or Rust. And so next, we want to do some math. Math in like adding two 64-bit integers in C translates into 2-3 CPU instructions. Again, it's super fast. Your CPU is amazingly fast at adding numbers together. I could tell it to add numbers by the it can actually add multiple numbers at once, like on a single core. Even before you get to the fact you have multiple cores, and it takes nanoseconds, and it's just amazing, right? But that's with C. With Python, so here's first it has to figure out which function to call for adding, and that takes some work. And then here's the function for adding two Python integers. So we're getting a pylong object star, another pylong object star, two pointers, the two objects somewhere in memory. And then it does some checks, and then it calls maybe another function, and otherwise it does some other checks. And then it has to create a new object, and it's just doing a lot more work. So again, math in Python is slow. And notice that most of this is for small numbers, the actual math you're doing is really still down at the bottom. You're just adding two integers that the CPU knows are integers. But to get there, you have to do a huge amount of work. And the reason is that Python, the interpreter, has a different memory representation than the C programming language. C or Rust or any language that's low level enough has a representation that isn't really that different from what the CPU is using. And so when you add two integers in Rust or C, that maps pretty much one-to-one most of the time to a add instruction for your CPU. Python uses much more complex objects because it's trying to do a whole bunch of things that C doesn't give you, and because it's trying to make things easier to use and more flexible. And that's nice as a user, but the downside is any interaction with a Python object requires converting from the Python object to something the CPU understands. So if we add two Python integers, we have to convert it to two integers that the CPU understands. We add them, then we have to convert them back into a Python object. And every time you're doing this, you're talking to the CPython APIs, which are written in C, but it's a whole bunch of overhead of interacting over and over and over again. And to take a step further, we can actually look at how memory is laid out for a C array versus a Python list. So imagine you have a 64-bit integer. That means it takes 8 bytes. Your CPU knows how to add two 64-bit integers. It has a built-in instruction for that. And a C array of 64-bit integers is just a consecutive block of memory. Each number takes 8 bytes. So number 1, 2, 3, and that's 8 bytes. And then the next number, 4, 5, 6 bytes, and so on and so forth. And so every time you want to find the next item in your array, you just look 8 bytes ahead in memory. You're just like adding 8 to get the next address to read from. When you read it in, you're just copying 8 bytes from memory into your CPU registers. It's very, very simple, and it maps the way C arrays are structured, maps to the way the CPU thinks about how computing happens. If you look at a Python list, it's a bit more complicated. You still have an array, but it's an array of PyObject stars. It's an array of pointers to PyObjects. And PyObjects are generic. So it's not even a list, it doesn't know that it's a list of integers. It knows that it's a list of Python objects. And then you go to the Python objects. Once you're there, you can say, okay, what kind of object are you? So you go look at this pointer, and you go look somewhere else in memory, and you say, are you really an integer? And it says yes. And then you say, okay, well, now we have 28 bytes of data, what type it is, and some ref counting, and some other bookkeeping. And somewhere in there's a data that tells you what the actual number is, but you have to decode it, as we've seen. The things like pylong from long and to encode it, and long from pylong, or some similar function to go the other way. And so it's much more complicated and interactive. And as an added bonus, storing a whole bunch of Python objects, Python list, Python integers, takes a lot more memory than a C array, because you have all that extra overhead. And so this means is not only are you slow because you have to do more CPU instructions, this extra memory usage can also slow you down because things don't fit as well in the CPU memory caches, or in a bad day because you start swapping and hitting disk, and then like you're having a really, really significant impact on performance. So Python lists of Python integers are just bad in terms of performance, bad in terms of memory usage. So now that we understand why Python is slow, we could start thinking about how to speed things up. So we know that operating on a C array is very fast. To iterate over it, we just jump forward 8 bytes at a time if it's a 64-bit integer. To do math, we just load the C numbers out of it. We don't have to deal with any Python APIs. So what NumPy does, give you an array, is it takes a C array and it does a Python object. So Python list is a whole bunch of Python integers wrapped in a Python list. A NumPy array is a single Python object, and inside it's just a C array. Excuse me. And it has a specific type. So you say, oh, this is an unsigned 64-bit integer, this is a signed 16-bit integer, what have you. You can't mix different types of numbers. They have to be single kind. You have to decide up front. But having done that, whenever you're doing some interaction with this array, doing some math, you could bypass Python altogether. When you're doing a sum, you say, it's a C array. I know how to sum a C array fast. And then once you're done with doing all that, you can go back into Python. But most of the time, you're just dealing with a C array. Doing mathematical operations at C arrays in bulk is nice and fast. Pandas series build up data frames are also NumPy arrays underneath. And that's changing a little bit in Pandas 2.0. Eventually, it's going to be a different data structure. On a fundamental level, it's the same kind of solution. You have some sort of data structure underneath that does not require any Python code to do stuff to, and you can therefore get fast operations. So for example, let's say we have a Python list of 1 million Python integers. If we want to iterate over this and sum it, first we have to do 1 million Python API calls just to get 1, 0, 1, 2, 3, 4, 5, 6, or just to get the first item, the second item. Either way, we're calling lots and lots of Python API calls. And then we are adding up Python integers, which again is lots and lots and lots of CPython API calls. And under the hood, eventually you're getting to the point where it's doing 1 million adds. and CPU instructions. Before you get to that, there's this huge overhead of bookkeeping and just turning things from Python objects into C things and back and forth, and it's all overhead. If you sum a NumPy array with NumPy.sum, in contrast, you start with a Python object and you say, oh, inside this Python object, I have a C array. That C array doesn't know anything about Python. As soon as I have that array, okay, you can say, okay, I don't have to think about Python anymore. These are just integers that I can sum really quickly using direct CPU instructions. You zoom through it. At the end, you have a number, and then you wrap that in a CPython object and you return it. And so you are interacting with the Python API, but only at the beginning and the end, and it's a fixed number. It doesn't matter how many items are in the array. You can have an array with 1 million or 10 million or 3 billion values in it. You only the fixed overhead from Python is the same, and it's very, very small in comparison. And so summing is much, much faster. So this representation allows us to write much faster. Now, just because you are operating on a whole array doesn't mean your code is going to be fast necessarily. So Python has a built-in sum function. So we can write our own version of summing that instead of using numpy.sum uses Python's built-in sum. Python's built-in sum is written in C, which is fast language, but it's still slow. And so why is that? When you use Python's built-in sum, it is a completely generic implementation. And it has some specializations a little bit, but it's still assuming it's dealing with a Python iterable object. And so a Python iterable object is a thing you iterate over and get Python objects using Python APIs. So Python's built-in sum doesn't know that what you have is a C array. From its perspective, it's saying, give me the next item using the Python API. This is a Python object. How do I add it to this other Python object? And it adds it. And it does have some optimizations for Python integers, but still it's calling Python APIs for every single item in your array because it doesn't know that it can bypass all the Python layer. It's designed to talk to the Python layer. So it's still doing slow operations. And we can see this in speed. If we measure summing with a Python for loop, it's 1.5 seconds. With built-in sum, it's 1.3 seconds. And with numpy.sum, it's 0.03 seconds. So it's not enough for your operation to operate on the whole array. It has to not call into Python at all to be fast. And this brings us to our definition of what vectorization means. And this is important because people talk about, oh, you should switch to a vectorized API to run faster. And it is true that vectorized APIs can be faster, but they aren't always. And so it's important to understand why. And so vectorization can mean two things for our purposes, and there's actually a third one that I will mention just because it can be confusing. So the first is a bulk API. A vectorized API is a function that operates on a whole array. So instead of saying a for loop where you go item by item, you say, here's a whole array, run it quickly. A second meaning is a fast API that bypasses Python. And in order to bypass Python, it has to be a bulk API that gets a whole array. But it also has to be implemented in a fast language, and it can't call back into CPython APIs for every item. So Python's built-in sum called back into Python for every item, and so it was slow. And so it was a bulk API, not a fast API. And there's a third meaning, which we'll discuss in just a bit. So if we think about how we're doing sums, if we Python for loop, iterate over your object, it's not a bulk API. We're operating item by item on every item in the list of the array, and it's certainly not fast. The built-in sum function that's part of Python is written in C, and it is a bulk API. You do pass it the whole array, but it's still slow because it's still calling back into Python. NumPy.sum on a NumPy array is written in C. It takes the whole array, but importantly, once it's doing the math, it's not calling back into Python. And so as a result, it runs quickly. And so that third level where you have both a bulk API and a fast API is where you get the huge speed ups over regular Python. And this is a bit of a digression. I'm just going to mention it. Sometimes you will hear C programmers, Rust programmers talking about vectorized functions. they mean something very different. They are talking about a thing called SIMD, or single instruction multiple data, where your CPU can add multiple things at once or multiply different things at once. It can process, if you're doing the same operation on a small array, it can do the same operation all of them at once, and then you can utilize your CPU faster. So if you're talking to a C or C++ or Rust programmer and they talk about vectorization, make sure they're not talking about SIMD. This is a completely different thing. It is not at all what Python programmers mean by vectorization. So we've talked about why Python is slow. It's slow because every operation involves converting back and forth from Python's representation to something the CPU can operate on. We've talked about how you solve this by having a thin Python wrapper around an array there's just a C array, and then our operations can just bypass Python altogether. And so now we can build on that, and we can think about how to write fast code using what we've learned. So first, you want to avoid built-in Python objects if you have a large amount of data. If you love, and in particular, I'm talking about numeric data. Processing strings is a whole other discussion because they're different. You can't rely on the same sort of optimizations working necessarily. So we're only talking about numeric data. If you're talking about numeric data, you don't want to use Python lists. You don't want to use Python dictionaries. You want to use stuff like NumPy arrays or Pandas data frames or other libraries that implement the same interface or the same kind of pattern. Some of them have representations that are basically the same as NumPy. Polars is a replacement for Pandas in some sense. It uses a different representation that actually Pandas is moving towards. And Polars also has a bunch of other benefits, but in general, using a representation lets you bypass Python when processing your data is where you get the speedups from. So for example, if you have some sort of CSV and you want to read the first column and store it as a bunch of floats, and then you're going to do some stuff with it, you could open the file with Python's built-in CSV reader, and then for every row, convert the first item in the row to a float, and then append to the list, and at the end, you'll have a list of floats. And this works. But it's going to be slow because all of these operations involve dealing with Python strings, and then creating a Python floats, and then it appending to a list in Python is also doing a whole bunch of work. It's going to be slow. As an alternative, Pandas has a CSV reader. You can just read the CSV in. If you're feeling extra ambitious, you can skip all the columns you're not interested in, and it'll be even faster. And this, for the most part, will bypass Python and load much faster. And so by avoiding Python objects and avoiding Python lists, we can get that structures that we can then operate on more quickly. Once you've switched to a better representation, you still also need to avoid iterating in Python. So a Python for loop, list comprehensions, genera comprehensions, anything that involves iterating, maps. In general, all these APIs involve treating your, you loaded all your data into a NumPy array. Then as soon as you go back to using a Python for loop, you are going back to using Python APIs to interact with it. So in theory, it could be faster, but in practice, you're using it in an inefficient way. And so you don't get any benefits from the more efficient representation, except maybe reduce memory usage. So if you're dealing with, even once you've loaded everything into this more optimized data structure, you still need to avoid Python for loops. And instead, you want to use vectorized or bulk APIs that do the iteration internally. Like you still in the end are going to iterate, but it's going to be, when you do a sum on an array using NumPy sum, the internal iteration is going to be in C, and it's going to bypass Python and run directly on the C array, and so everything will be faster. If you do a Python for loop, everything will be slow. So for example, here's a function that calculates the mean distance from 0. So for every item we calculate in an array, we calculate the absolute value. So if it's negative, we just convert it into a positive number. We sum those all up, and we divide by the length of the array. And so doing this with a for loop is slow, and we can switch to a version using NumPy. And first we create an absolute version of the array, and then we call mean on it. And that will be fast because we're not using a Python for loop, which means we're actually able to do these operations quickly in a fast language. The problem is this actually has much more memory usage than the previous version. And in particular, when we call numpy.abs, when we get an absolute value of the array, it creates a new temporary array, and then we call it mean on that. And so we're actually doubling our memory usage when we use this pattern. And I mentioned because vectorization does not come without costs. Sometimes it will result in using much more memory, and that can slow you down in other ways or raise your costs in other ways. And so if you find yourself in a situation where the vectorized solution requires you to create a whole new array as just as a temporary value, and the for loop would make much more sense. There's a library called Numba that is a different way of speeding up computations, and it's integrated with NumPy arrays. And if you use Numba, you can write for loops that don't have this problem of having to allocate a whole new temporary array just to avoid using. Another thing you want to avoid is calling back into Python. So for example, let's say you have a pandas data frame. So you can think of it as a mapping from column names to one-dimensional arrays. You have a column called counts, and you want to get absolute values of those counts. You can call map on a data frame on the series that gets returned here. And we're passing a numpy.apps, which is potentially a vectorized function. But you can also call it an individual items. And the map function accepts a generic Python callable. So and it is often called item by item, depending how you use Pandas' excitingly complicated APIs. And so if you're calling a generic Python callable on an individual generic Python item in your array, that means somewhere in there, it's calling back into Python for every single item in the column. And so even though the function itself is potentially fast, the fact that you're calling back into Python in order to do a Python callable and a Python object, that takes away the speed benefits. Because in theory, everything is slow. In practice, we're just bypassing it by operating item by item using Python objects. And so what we want to do is we want to do a vectorized call where we're calling numpy.abs on the whole array, and then it will do the iteration within itself instead of relying on getting one Python object at a time. And so then it can bypass Python APIs and just operate on a C array. And this can be a little bit tricky to notice because NumPy functions can often take both individual numbers and a whole array. You can call numpy.apps on -3 and it'll give you 3. Or you can call numpy.apps on a whole array and then it'll do apps and item and give you a new array. So you have to be on the lookout in places where you think you're calling a fast function, but you're calling it one item at a time, which means it has to go back and forth into Python in every iteration and slow things down. So to summarize, if you're dealing with large amounts of numeric data, process it quickly. Avoid built-in Python objects. Instead, you want to use things like NumPy arrays. Avoid iterating in Python. Instead, you want to use bulk vectorized APIs, like NumPy's functions. Avoid calling back into Python. If you are calling back into Python, and then you've undone all the benefits you get from having a better representation, we're back to doing slow operations. And instead, you want to use bulk, fast, vectorized APIs, operate on NumPy arrays or similar data structures. So that's my talk. The slides are available at pythonspeed.com/pwc2023, or they are in theory. If you're watching this live, for some reason, they're not up. I have to fix that. So it might, sometime this afternoon, I will fix that. You can email me if you have any questions. And I also work on a speed and memory profiler for Python data processing applications called Sciagraph. It's sciagraph.com. And in the end, there's no, if you want to make your code fast, knowing the kind of things we've talked about is extremely helpful. And you can just start with a much faster baseline. But there's always going to be reasons that your code is slow that you were not aware of, that you didn't expect. And finding why your program is using high memory is even harder. And so a profiler is really helpful in finding these bottlenecks that you just wouldn't ever expect. And Sciagraph is my attempt at that. There are others, but when you're dealing with performance, some sort of profiling, some sort of measurement is really critical.